Welcome to week 4, everyone. We have a busy week ahead of us. On Monday this week and on Wednesday last week, you've been introduced to pointers, and so hopefully that has blown your mind, but hopefully not made you too confused. If it has, we will go over that in section today, as well as we're going to do pointers. We're going to go over the stack, which you've talked about in lecture already, when we're going to hint at things to come on Wednesday and beyond in terms of memory management. And finally, we're going to talk a bit about the Stanford Portable Language, which is the library you guys are using this week to implement the problem set. So as I showed you all last week, I wanted to put this slide up again because this is a list of the resources that are available to you. CS50. These are what we give you out of the box. And these are incredibly important for what the next slide will show. But before we get to the next slide, I want to go over these again. For every lecture, there are notes that are taken. So it's a digest of the lecture, but it also has code snippets in and helpful tips and tricks. So if you want to review lecture, hopefully you didn't miss lecture. But if you did, you should rewatch it. But when you want to review lecture, definitely check out those lecture notes. There's also source code online from every lecture. cs50.net/shorts are short 6 to 12 minute videos. You guys have seen many of them. There are also videos we don't assign to you, but cover topics that are covered in lecture in this course. So if you want a refresher on those topics, do check out these shorts. Study.cs50.net has primers on a ton of topics. It has videos. It has practice problems. It is a fantastic resource. Come any questions, but also quiz time. A couple more resources. There is the man command in the terminal that gives you some information on a particular function or command. There's Google, my favorite resource, one of my favorite resources. My favorite resource is the last one, which we'll get to in a second. There's cs50.net Discuss. That's our classes forum. There are office hours Mondays through Thursdays, 8 to 11. There are also online office hours for extension students. And finally, if you need anything, have any questions, comments, or concerns, you have my contact information. Get in touch with me, please. So as I hinted at, next Wednesday, a week from tomorrow, is your first quiz, quiz 0, because in computer science we start counting at 0. More information will be provided in lecture tomorrow, and a handout will be posted eventually online with details, more specific details, in particular the location of quiz 0. But it'll take place next Wednesday instead of lecture. There's no lecture next Monday because it's a holiday. The quiz will cover all of the material from week 0 to week 5, so through this week, through lecture tomorrow. Material includes the lectures. Material includes sections. Material includes the problem sets, and especially those beginning parts of problem sets where you're walked through some background information on what you're about to cover. Do look through those problem sets. To help you all with the quiz, next Monday, even though it is a holiday, the course will be hosting a course-wide review session. Video of the course-wide review session will be posted online if you aren't able to make it. In addition, next Tuesday in section, we are going to be doing a ton of quiz review and hopefully playing some Jeopardy as well. But we're going to be going over, answering all your questions, but I'm going to come with a lot of helpful questions and information based on 10 years of quizzes. I have a pretty good idea of what's going to show up and how questions are going to be asked, so we'll go over those in section next Tuesday. In addition, I didn't put this slide up last week, but this is something we did last week. This is how we approached a lot of the coding problems we did. So I wanted to distill out our approach into some simple steps that can help you with solving a coding problem. So remember last week we coded binary search. And the first thing we did when we wanted to code binary search is we thought about in our heads how it worked. We didn't draw a picture in class, but I asked everybody to watch the short video, which did have a picture representation of how binary search worked. So the first thing we really wanted to do to understand something is draw a picture, to understand its logic, to make sure we know how this thing works. The next thing we did do in section last week was we took our mental model and we turned it into some pseudocode. Pseudocode, again, programming like syntax and words, but not C code, not even specific to C. We just took our ideas and took the English we used to express it and wrote it out in some sort of program-looking way. So that's just the logic part. We took care of our logic first. We broke up this hard programming problem into 2 parts, and we took care of the logic part first. And then we approached the syntax part. Remember, after we drew up the pseudocode, we picked out parts of the pseudocode that we knew mapped on to specific elements in C. For example, for loops, if conditions, or greater than or equal to operators. And finally, the last thing we did, the very last thing we did, was actually code this program in C. So we're going to go through this process again today in a relatively large coding problem that will take up the bulk of second half of section. but I wanted to lay this framework out here for you guys. It is how we've been approaching problems in class and how probably you've been approaching these problems on your own outside of section. So I'm going to leave this up here, and we'll refer back to this when we're coding later today and go through systematically through these steps. Finally, feedback. If you have any feedback for me, the website is at top of this slide, sayat.me/cs50. Give me some feedback. I got some fantastic feedback from you guys last week. You said you really liked the pseudocoding and coding we did. You also, somebody gave me a study, a link to a study that has shown that waiting 3 to 7 seconds after asking if anybody has questions is the optimal time to wait. So if you have your stopwatches out, today I'm going to try and wait 7 seconds after I ask if anybody has any questions before moving on. So before we move on, does anybody have any questions so far? Control room gave me 7 seconds. OK, nobody had any questions, but feel free to ask them if you do. First, this week we are going to cover pointers, as we hinted at the agenda at the beginning of class. Pointers you've seen in lecture, they have probably melted your mind. That's OK. That's what they have done to hundreds of CS50 students before you. So over the next 10 to 30 minutes, we are going to go through these pointers slowly and systematically. If at any point you have any questions, please ask me. I guarantee that your peers in this section and watching at home have the same exact questions. So let's talk generally first, before we dive into pointers, about variables and data, which we've been using before. In addition to having these things up on a slide, I'm going to draw these out. So as this slide says, data in memory has both a value and an address. So we're going to represent something in memory. Remember last week, when you've seen arrays being drawn, we generally draw them as series of boxes. So we'll just draw one variable as a box somewhere in memory. This box, in this example, we'll call it x. And it has a value. In this case, we're initializing the variable to a value of 50. You'll also notice that in addition to just a value, this variable x has a location in memory. Indeed, as you are probably somewhat aware of, memory has a finite amount of spaces. There's only so many boxes inside your computer where you can store things. And better yet, so you know where things are stored, each box has a specific address, a specific number where you can find it. Just like freshmen all have their mailing address in the Science Center, every box in memory has a specific address. When you go to that address, you can get what's located there. So I'm going to call this totally arbitrary. I'm going to be totally arbitrary with the address of this variable, but I'm going to say the address is 123. Now, I didn't just write 123. I wrote 0x123. The 0x part means this is a hexadecimal number. And we are not going to talk about hexadecimal a lot today, but know that when we refer to memory addresses, we refer to them in hexadecimal. So whenever I'm talking about an address, I'll put that 0x, and that's just saying 123 is a hexadecimal number. It's in base 16. It's not in base 10. Does anybody have any questions so far? Perfect. So that's one variable. We've seen this before, but now we're starting to go under the hood and see what's actually happening. So pointers. The cool thing about pointers is that unlike a normal variable that have some value, some integer, some character, maybe a series of characters if we're talking about an array, the value that a pointer has is an address. So let's, up on the screen, we have the int x equals 50 that we created before. I've already drawn that box. Let's also draw a box. This is going to be, oh my goodness, we need a new marker. Not much better. But we're going to call this box, this is the variable called pointer. Pointer also has an address. It's at a different address. It's a different variable. It's not going to be on top of the first one. You can't put two things inside of a mailbox. You can't overwrite the initial one. So we're going at a different address here. We'll give it the address 456. But pointer's value is going to be an address. And in this case, it's going to be the address of the x variable. So inside pointer, we're storing the address 123. And the syntax I use to write that, we're going to go over the syntax in a second, but know that the syntax on this slide is the syntax you would use to set this situation up. Before we get to the syntax, though, I want to make clear to everybody and make sure everybody understands that pointers, as distinct from variables, have an address as their value, not an integer or a char. So far, so good? Generally, also, when we're drawing these things, I'm not just going to draw the address in here. I'm going to take an arrow from this box to the other variable that it's pointing to give the sense that if I were to look at the address 123, if I were to use this pointer to find what it's pointing to, I would get this box over here. I would get the number 50. Yes, question?
So if pointer stores an address, then how do we choose whether it's an int star or like a char star or whatever? Because
can you repeat the middle part? I lost you.
How do we choose whether it's like an int star or a char star or whatever if all it stores is an address?
Good question. So how do we choose what it's actually pointing to if it always stores an address? If instead of writing int star right here, I wrote char star, it would be pointing to, we would have, that is what we would write if we wanted it to point to a character. Deep, deep down in the ones and zeros world, that int, that char doesn't really matter. But in terms of C, it does want you to be pretty specific in terms of the type of thing you're pointing to. So at the level at which we're programming, we're going to write the type of thing we're pointing to, even though it's always an address inside this box. OK. Madhu, did you have a question? OK. So now we're going to look at some syntax for pointers. The first line on this slide, int star space pointer, initializes and creates, not initializes rather, doesn't set it equal to anything, but it creates this pointer. So in terms of my diagram, let's go to this side. That first line, int star pointer, creates a box. This box is the pointer variable, and it's at an address. We'll give it a different address, 999. So that's all that line does. We've seen this before. That's like anytime if I were to just write int x there, it would do the same exact thing, create a box called x. In this case, we just are creating a bit different. We're giving it a different type. So it's not going to be an int, it's going to be an int star. And so this box will be a little bit larger or a little bit different than if it were to just be a char, for example. Because chars, recall, are only 1 byte in memory. Pointers are 4 bytes. So this box will look a little bit different if we write int star as opposed to char. But other than that, we're creating a box and it's at a specific address. That's all that first line does. The second line of code, int x equals 50, again, creates another box, x at a different location. We'll give this location 111. And this is actually initializing the pointer in addition to creating the box. We're putting a 50 inside this box. The third line of code, pointer equals address x. Now that address operator means a very specific thing. Whenever we put the ampersand in front of a variable name, we are saying, give me the address of that variable. So when I write ampersand x, that's saying, give me the address of x. In this case, 111. Yes?
So would it be acceptable if we happen to know the address of this particular variable to just say pointer equals OX111?
So if you knew that this was at 111, you could write pointer x equals this hexadecimal number, but I can't see a way that you would ever know what it is.
Yeah. Okay.
So that's why we use this syntax.
Yeah.
But again, that ampersand x, ampersand is saying, give me the address of this variable. And just like any equal sign does, that's storing that value inside pointer. So whenever you see that ampersand, think, this is giving me the address of this thing. Ampersand x is giving me the address of this x box. Again, if we did ampersand pointer, what would I get?
Address of the pointer.
The address of the pointer, what specifically?
OX999.
999. Ampersand pointer would give me 999 in this case. Ampersand in front of any variable gives you the address of that variable. Of course, I don't really care about the address of this pointer. I care much more about the address of this variable. Finally, the last symbol we're going to see is actually the same symbol, that asterisk. But in this final line, it's used a bit differently. Notice how in this last line, it's next to the variable. As before, it was next to the type. It was part of this type. We're creating this type integer pointer. Now, the star means something a little bit different. It means go treat the value in pointer treat the value in this variable like an address, go to that address, and give me that value. So the star means, again, treat the value in pointer as an address, go to that address, and return that value. In this case, that value is 50, so this line would printf 50. Yes?
So if we tried to do that on something that wasn't like declared as a pointer, like on X, and the value is 50, would it try to go to address 50, or would it just give us an error?
So if we did star X and tried to printf that, what the compiler would do, or what the program would do when it was running, is it would treat 50 like an address and go to address number 50 in your program. Generally, when you're going to these random addresses, you're not going to go to an address where something is like nice there. You're going to go to a really bad address that you're not supposed to go to, and your program is going to crash. So yes, you're exactly right. It would do the same exact thing, but when we try to go to addresses that we haven't asked for, or we haven't declared, or that are just random addresses, we almost always get in trouble and our program crashes. Did that answer your question?
Yeah, I guess I have another one now.
Uh-huh.
So if you could just do that, and it would go to that address, what's the point of declaring a pointer as a pointer if we could just say pointer equals ampersand thing, and then it would be like a meaningful address, and then we could go there, right?
Can you repeat the question?
So like, why do we have to declare the pointer as an int star if it would work to just declare it as like a regular int, because it would still have, a thing that could be then dereferenced, right?
So why are we declaring it as an int star rather than just like an integer and saving this number in it?
Yeah.
Because when we use things, great question. When we use things, whenever we're using a pointer and going to treat something like pointers, other things are going on that I'm not going to go into now, that it helps if the program knows that this thing is a pointer.
Okay.
It will treat it differently in some other ways that is irrelevant for us. But if we are going to use it like a pointer, we should say we're going to be using this as a pointer.
Okay.
Okay. So that is basically how the pointers work. It's not much more complicated than that, but unfortunately it becomes a lot more complicated when we put it into practice. So next, we are going to do something quite large. Instead of just throwing a couple lines of code on the line, I put up 4, 5, 6, 7, 8, 9, 10 lines of code. And rather than coding these out on your computer or running this program on your computer, I want you to take out a sheet of paper and a pencil or a pen and figure out what each of lines of these codes do. Start with the left column, working from top to bottom, which initializes a lot of these variables. And then go through each line of code in the right column and figure out what happens. I'll give everybody 3 minutes to start this on your own, and then we'll go over this as a group. get started going over this as a group. It's okay if you haven't finished. I'm going to start with the left-hand side of the column, and then I'm going to invite you guys up here, for the brave of you amongst you up here, to execute one line of code on the right-hand side of the column, and then we'll work our way through. So first, that first line of code, int x equals 2, comma y equals 8, comma z equals 12, creates 3 variables. I did it all on one line. That's a handy syntax for creating multiple things of the same type on one line. So we have 3 boxes. Can everybody see those 3, or is that too low? OK. We have x, y, z. And in x, we get 2. In y, we get 8. And in z, we get 12. Pretty standard so far. Next, we're creating another box, another variable. This is an int pointer. It's called pointer x. So we'll draw that over here. And what are we storing inside pointer x?
The address of x.
The address of x. In this case, I don't know the address of x. It could be anything, but I'm going to make something up now to make it easier for us. We'll put x at 1, 1, 1. So this gets 0x, 1, 1, 1. And we'll give it a nice arrow to signify it's pointing to x. Likewise, I have pointer y and pointer z. They get values. We'll give this 0x, 2, 2, 2, 0x, 3, 3, 3. That's our initial setup on the left-hand side of the column. We created 3 integers, and we created 3 pointers. Inside each pointer, we save the address of one of the 3 initial variables we created. Now, on the right-hand side of the column, we are using that asterisk, which symbol, in a number of different ways. Not all of which are to use it to dereference something or to go to a specific address and return the value there. So can someone tell me what the first line of code does? Why didn't somebody raise their hand who hasn't spoken yet? You?
It set z to 16.
It set z to 16. So z equals x times y. In that case, it's just multiplication we're doing. So z equals x times y. 2 times 8 is 16. Perfect. So we'll update this. Z equals 16. That second line of code, x space star equals space y. What does that line of code do? Jeff?
X equals x times y.
Exactly right. That's shorthand notation for x equals x times y. You've probably seen things like x plus equals y. That's x equals x plus y. In this case, we're doing something a bit different. X equals x times y. So then what do I need to update here? X is 16. So those changes in green are what we have done so far. Next, we have y equals star pointer x. Can somebody walk me through what this line of code does? Akshar, what does this line of code do? Walk me through from the beginning.
So it takes whatever pointer x is pointing to, the value that's being pointed by that,
OK?
and it stores it in y.
Excellent. I'm going to repeat that again. You did a fantastic job. But so we can emphasize it. That star means treat the thing in that variable like an address and go to it. So treat the thing in pointer x like an address, go to it, take that value 16, and then we're just saving it in the variable y. So now y gets overwritten. And it is now 16. The next line of code, star pointer underscore x equals x times y. What does that line of code do? Again, if you're a little bit lost here, evaluate it from right to left. So Madhu, what does the right-hand side of that do?
So the right-hand side just multiplies whatever is in the boxes x and y.
And that's 16, 16, so what's that equal?
256.
256. So and where are we saving 256?
You're saving it in whatever pointer x is pointing to, which is the x box. So now x becomes 256.
So the star, again, means go to. We go to what pointer x is pointing to. It's pointing to x, and there we're saving the value 256. Any questions about that specific one? We haven't seen the star used on the left-hand side yet of an assignment operator. Okay, so that's the 4th line of code. The 5th line of code. Can somebody who hasn't spoken yet give me the 5th line of code or walk through it with me? Annie, what's it do?
Change the value of pointer x to the value of pointer y.
That's exactly right. The value of pointer y is this address right here, and we're storing that in that variable pointer x. So this becomes 222, and so I'm going to move the arrow too to signify that it now has a different address. So now pointer underscore x and pointer underscore y have the same value. That's what that line does. So essentially, they're both pointing to y. If we just had our pointers and we didn't really know the variables, we would have lost x. But thankfully, we have x saved in this function, so we still know where x is. But we'll see that problem coming up later on, that if we lose a pointer to something, we might not actually know where it is or be able to recover it. But that's for the future. So for right now, that's exactly right, Annie. And finally, that last line of code. Can somebody give me what the last line of code does? Yes?
It multiplies what is in pointer y, so like 16 times 16.
Sorry, 16 is not in pointer y.
Well, it goes to that address, finds it, and then multiplies that by the same thing does the same thing with pointer c, multiplies the values and stores it in x.
Exactly right. So what do I need to update?
X.
What should x be?
The top left corner.
And what do I change it to? Sorry, we'll go back up.
It should still be the same.
Yes, it actually still equals 256. But that's exactly right. Let's break this down. We'll see right here, this line, this thing in parentheses, star pointer y that treats what's in pointer y as an address, goes to that address, takes the 16, so now we have a 16, and we're multiplying that by the same thing in z, going to that address, taking a 16. 16 times 16 is 256, and we're storing that inside of x. X already happens to equal 256, though, so we're not going to make a change. So you don't have this file right now, but in the source code for this section, which will be posted online at cs50.net/sections, I have written all of this up, exactly what we did. And I actually included some other information right here, which we're going to go through in a second. We do these operations, as you can see right here, and then print out the resulting value of the specific variable that has been changed. So this code's already been written. I'm going to run this code. And now let's walk through the output. Let's start at the beginning. Value of x is 2. That should make sense. That was what we initially initialized it to. Address of x is this crazy thing. Again, we see, however, even though it looks a little bit crazy upon first inspection, we see that 0x right there. This is a hexadecimal number. And then we see all of this crazy stuff. There's a B and an F and also a C in there. None of those are normal 0 through 9 digits. But because hexadecimal is base 16, you actually need a couple of other symbols to represent each digit. So again, we're not going to talk about hexadecimal too much, but know that when you're writing hexadecimal numbers, you'll see anything from 0 through 9 plus things from A through F. So these are, even though they're not all 0 through 9 numbers, this is a number. This is an address. And it could be expressed in base 10 if we wanted to. The value of pointer x right here is also a hexadecimal number. And what is it the same of? What is this number the same as?
Address of x.
Address of x, right? The line right above it. Those two addresses are identical, and that's what we expect. The address of x is the value of pointer to x. Next, we have the address of pointer x. And that is, again, some random number. It actually, if we're going to inspect it, we notice that it actually looks, shares a lot of the same numbers as the other ones. It's different, but it shares a lot of the same numbers. That's maybe recollect talking about buffer overflow errors, when you can write over things that are close to you in memory if you go beyond the bounds of an array. Again, we're not going to talk about that right now, but for those of you curious, these things are actually pretty close to one another. These boxes are pretty close to one another in memory. And finally, pointer x points to the value, and of course it's 2. I did that star. We followed the address in pointer x initially, and it returned the value of x. Finally, we see exactly what we just did. First z is 16, then x is 16, then y is 16. X eventually becomes 256 right here. And again, x is not changed by that last line of code. It remains at 256. So if you want to repeat this on your own, once again, or go through it or change some of these values up, I've already written this code. You can make the changes to the code and see how those changes affect or see how those changes actually play out in real life. Before we move on with pointers, does anybody have any questions? OK, can everybody take one hand and put it up in the air and close your eyes. Put your right hand up in the air as a fist and give me a thumbs up, thumbs down, thumbs middle, how comfortable you are with pointers so far. Close your eyes. OK, you can put your hands down and open your eyes. Thank you. So we're going to move on. We're going to keep talking about pointers. We're going to talk about them in a little bit of a different context. We're going to talk about arrays and pointers. And remember last week I blew your minds. So somebody's brains, they left them here on the floor. I was pretty sure I blew that person's mind. That was a bad joke. I'm going to work on that. But anyway, strings we found out were arrays. Arrays are actually pointers. What do I mean by that? Well, if we create an array of 6 characters, which this line of code does right here, char array, open bracket 6, close bracket semicolon, again, creates an array of 6 characters. Fill it. I have a picture of it right here. These boxes. We see that I filled it with some characters and the null terminator at the end. And down below, this is where I'd like you to direct your attention. The very first box, we've done this before. We've actually done this in every problem set. I can refer to the very first box in this array as array bracket 0. We've done that a million times. I can actually refer to the same box another way. I can refer to it as star array. Because array, if we were actually to print out what array equals, array is an address. And it's an address of the first box in this array. So that star operator treats what's stored in an array as an address, goes to that address, and returns the value there. Star array will return f, just like array bracket 0 returns f. Again, everywhere we've been writing array bracket 0, star array would have done the exact same thing. In fact, array bracket 0 is just our sugar coating of what's actually happening. It's really star array is the more correct way, if there is one correct way, to think of what's actually happening. So that's all well and good, but here's where it gets fantastic. We go to the second character here. This 0 should be an O, but we'll give it a 0. We've referred to that before. The second box in an array is array bracket 1, whenever we've iterated through an array. There's another way to refer to it, and that's down below. That's star, open paren, array plus 1, close paren. So because arrays are laid out, these boxes are all right next to each other in memory, star array goes to the first one. So if we're going to take array, that address, add 1 to it, and then go to that new address, it's going to be the thing right next to the original address. Yeah?
So if array was, instead of being chars, it'd be ints, then you'd have to like increment by 4 every time, or?
That's a great question. Let me draw something first, and then I'm going to answer your question. So to draw this up on the screen really quickly before getting to your question, we have our array. And it goes on, but I'm only going to focus on the first couple of ones. In memory, there's a box that we created when we initialized this array. This is the array variable. And it is an address. It is, in fact, the address of the first thing, the first box. So this box is somewhere. These 6 boxes are somewhere else. So when we do array bracket 0, we're going to get the first thing here. And when we do star array, we're going to get the exact same thing, the value that array is pointing to. When we do array bracket 1, we're going to get the second box. But we're also, because the pointer is outside this parentheses, first we're going to add 1 to this address, and then we're going to follow that and give us the second box, and so on and so forth. Array plus 2 is going to add 2 to this address here, because again, addresses are just numbers represented as hexadecimal often. So add 2 to it and follow that to the third box, which happens to be, as you can see, 2 spaces away from the first box. Hopefully that made it less confusing rather than more confusing. But did that make it more confusing? Again, I'm going to get to your question in 1 second. Did that make it more confusing for anybody? Or does anybody have any questions about this idea of arrays as pointers? Fantastic. Also, be fantastic if you had questions. But moving on to answer your question. So the question was, integers in memory take up 4 bytes. So 4 boxes. If we think as 1 box is 1 byte, integers take up 4 boxes. So say these are integers now. This is an int array right here. Rather than, I'm going to make up some random addresses. So if this was an int array, the first one might be at 10. It's 4. The next one's 4 boxes over, because integers are 4 boxes big. So this one would be, there'd be 10, 11, 12, 13. So this one would be at 14. This one would be at 18. This one would be at 22, and so on. So chars are 1 byte. They're right next to each other. So this math we were talking before works perfectly. But you just brought up the case of ints. Well, if I added 1 to this, it would go to 11. It'd be in the middle of this int if I followed it like really specifically like that. Was actually going box by box in memory. The cool thing about this type of pointer arithmetic is the program is smart enough to know what you mean. When you're adding 1 to a memory address that is pointing to an integer, it's not actually going to add 1 block over. It's going to add 4 blocks over. It's going to scale that number for you by the size. And this goes back to Curtis's question, why do we do int star rather than char star? Was that your question? Somebody asked that earlier, right? Why do we do int star rather than char star if it's going to be an address no matter what? And that's to help us with this type of pointer arithmetic. If we declare something as a char star, but it's really going through integers, when we added 1, it would only move 1 box over, rather than the 4 we'd logically expect it to move over. So again, in pointer arithmetic, when we're treating these things like addresses, then adding or subtracting to them, and then following them to figure out what's going on in memory, the number we add to them gets scaled by the size of the type of thing they're pointing to. So if they're pointing to an integer, I know I'm repeating myself, but if they're an integer, you're actually going to move 4 boxes over each time. If they're a char, you're going to move 1 box. If they are a long, which is 8 bytes, you're going to move 8 boxes over. Whatever the size of the data type, who knows? Doesn't really matter for our purposes. All that we need to know is actually this math right here, just adding 1 will get us to the second box regardless of what type of thing is in that second box. Okay, I hope there are some type of questions here because that was a lot. And I could not have done a perfect job at explaining that. Really? No questions? For the audience at home, there we go.
So if you were to make an array in a function and you wanted to return that array to something else, how would you return it?
Excellent question. So if you wanted to make an array in a function and then return that array, so we'll say we'll make an array in a function called by main. Main calls this function, and this function creates the array, then returns it to main. Now, we've seen something similar to this before. Where have we seen something similar, where main creates the array, and then the function manipulates it?
Game of 15.
What have we written before that's done that?
Sorting.
Sorting has done that. Game of 15's also done that. In sorting, we passed in the array, the haystack, and then we sorted it. by destructively updating different parts in that array. So we took our original array. Remember, one of the parameters to the sorting function was the array.
Wasn't that a global array?
Right, so yeah, we're going to get back there. But had it been created in, was it a global or was it created in the function? Let's look. We can answer that.
That was global.
Fine. Oops. So it looks like it's not a global array. It is created right here on this line, an array of integers, and then it's passed to our sorting function. So it isn't a global array. It's created in main, passed to our sorting function. Our sorting function destructively updates it and returns it. As we can see up at top, sort, oh my goodness, sorry.
The sort just returns whether or not it found it.
Right, sorry. Sort actually, let's open that up, gedit. Sort is void. Sort doesn't return anything because sort destructively updates the array, the original array. So that's what we've seen before. But your question was, what if sort actually creates the array?
Or returns the
Okay.
updated array or something.
So
like that.
another thing that could have been done was main called a function. That function's job is to create an array of something, an array of integers, and then return that array it's created to main. So, as we've seen before, when talking about the stack, which we're going to talk about a bit later today, once a function returns, everything that was created in that function, all of its local variables go away. Right? We've seen that idea of scope before. That's why we've created global variables sometime, to escape this problem of things going away when their functions return. So what you would do in that case is the function would create the array not as a local variable on the stack. It would create it in a different part of memory that allows things to be saved even when functions have returned and the function frame, the stack frame, has left the stack. So I'm going to use some terminology here. You're not going to hear about this till tomorrow, but that area of memory is called the heap, and I don't want to go into that. But what that function could do, again, to oversimplify potentially, is create that array in a different space of memory that actually stays there for as long as you want it to stay there, and it'll pass back to main a pointer to that array saved in that other part of memory. So it makes some boxes somewhere else that don't get destroyed when the function returns, and passes back to main an address to that set of boxes. That's probably not a sufficient enough answer to your question, but that will be explored more tomorrow when you guys talk about the heap in lecture. Okay, so let us move on. Oh my goodness, that's a dolphin. How adorable is that? God, they're my favorite animal. So they are indeed adorable. I have 3 dolphin stuffed animals, but enough about me. So you all have your computers open in front of you. Here is your coding assignment. We're going to start with pseudocode, though, so don't get too excited. You need to write a program that takes one and only one command line argument, and that's the number of dolphins to be trained. That number should be greater than 0. Next, you're going to allow the trainer to enter an age for each of these dolphins. Each age, again, should be greater than 0. And all of these ages should be stored in an array. To get an age, however, you need to call a function with the following prototype. Int star space get age parentheses void close parentheses semicolon. Finally, I want you to print out the age of the oldest dolphin. So again, before you start writing in code, have a sheet of paper or have gedit open if you want, and write out some pseudocode for this. In 3 minutes, we're going to go over the pseudocode. You'll have another 3 minutes to code it, and then we'll go over coding it together. And if you have any questions, because this isn't clear, raise your hand and I'll come around and I'm happy to answer your question. But take 3 minutes to write pseudocode to make sure you understand the logic of this problem. let's take a stab at the pseudocode as a group. I'm going to write this on the board as you give me the pseudocode. Who would like to give me the first line? First line is maybe the easiest, so if you haven't participated yet, start here. Avi, what's the first line of pseudocode?
First line is to check for the number of arguments that you get.
Exactly right. Check number of arguments. First thing we need to do. Next.
Check that command. The first argument is greater than 0.
Check that the first argument is greater than 0. Yes. Next line, go ahead.
Then you'd probably want to store that command line argument into a variable, or you could just go to the next step.
So yes, we are, again, we'll have a string here, but we want an integer because it's a number, so we need to make the string into an integer. That's right. So we'll write that string. Whoa, look at that marker. That's the second thing we need to do. Take the string and turn it into an int. What's next?
Create an array of ints with the size of the second, or the first command line argument that's not the program.
Sorry?
Yeah, just create an array of ints and make it the size of the command line argument that you got.
Create array of size, we'll do arg. Whatever that argument was, okay? What's next? So we have the array. Allow the trainer to enter an age for each dolphin. To get an age, call a function with the following prototype. So we have our array. What do we need to do? Yeah?
Oh, well, I was going to say for n dolphins.
Okay, so
For whatever.
I'm going to write for each.
Okay.
For each dolphin, what do we need to do? Go ahead.
Oh, call the function.
Call the
age.
function. Okay.
In pseudocoding, should you define functions like in a separate block of pseudocode?
So yeah, let's do a separate block of pseudocode over here, pseudocode for getAge. So this function, for each dolphin, we call getAge, and getAge returns something. So where should we put the thing we're returning?
To the
Right, it returns an int pointer, right? That's the return type, according to that function prototype. So where are we putting that int pointer?
Into the array.
Into the array. That sounds great. Call getAge, put return value in array. So let's pause getAge for a second. We'll come back to that, and I'll let you start me on that, Marcus. But we've gotten each age, we've put them all in the array. What do we do at the end? How do we finish main? What's the last thing we need to do? Alden?
We could sort them and then print the largest one.
We could sort them. Yes, so how do we sort?
I mean, you could just like.
Do we need to sort here though?
I suppose not.
Okay, you did this before. What was the first way you wrote search for?
We could just like check each one against each other one.
Let's do that. So let's search through each one and just keep track of the oldest age. Search for oldest. And then what do we need to do with the oldest?
Return it. Print it out. Sorry.
There we go. Exactly right. Print out oldest. Okay, Marcus?
Track of the oldest as you add them.
Okay, search for oldest. So we could keep track of the oldest as we add them up there. Call getAge, put return value in the array, and then see if this is the current oldest one, maybe save it in a different variable. Mm-hmm. That would work as well. That might actually save us a trip, but this is fantastic. I'm gonna leave this up here for now. Okay. But if you want to, in your implementation, take that step further, that would be great. Marcus, let's do getAge over here.
Okay, ask the user for an age.
Ask the user for an age. Okay. Can everybody see that? Over here? Okay, ask user for an age. Keep going. You got this.
I guess I don't really get why it's better to return an int star than just an int. Like than to just return the age to store it.
It's not necessarily better to return. It would work just as well returning int, but I want you to return an int star.
Okay.
Okay?
Yeah, I don't really know what.
Okay, does anybody have any thoughts? We asked the user for an age. We're getting an integer. Okay, so why don't we pause here? We're going to figure out we're going to go to our next step in the logic, map these things onto C, and then you guys will code that first part, and we'll code all of that together, but in particular get age. And we'll figure out what's going on with that int star. Okay? So before we do that, before we jump into C code, can somebody point out some things they see in our pseudocode that would map onto regular code in C? So some things in pseudocode, some words you see, some indentation you see, some things that give you some hints about how to code this in C.
For loop.
Where?
For each dolphin.
Okay. There we go. We got a loop there. What else? Madhu?
The string to int thing would be a to I.
Okay. So we've seen that function before. Other stuff we see. Exactly. Not obviously, but hopefully we have some familiarity now with printf. What else? Yeah?
Creating an array is just declaring an array.
Okay. So of size arg. That's right. I don't know what to write that as. Yeah. But yes, declaring one, another word for creating it. Any other things we see up here? Structures we know to code. What about that line, search for oldest? What kind of structure might that use? Alden, you suggested it.
Just search.
Okay.
So like just a loop.
A loop. So this search, you're probably talking about linear search right here, so it's probably just using a standard loop going through everything, which is why Curtis suggested we could put it in the previous loop. Any other things we see? Check, number of args. How do we check something?
If statements.
That's an if condition. So why don't you get started coding this program? You have the pseudocode up here. Start writing it in C code. Again, we're going to figure out what's going on with that in star and how we can actually write this program so that it conforms to the specification I've given you. If you want to, however, start with just int. Get void. It just returns an integer. If that helps you get going, just code that. Code it as just the return type as an int, not as an int star. But then we are going to turn it into int star again so we can conform to the specification, also explore how one might actually get at what Jeff was talking about earlier. So take 3 to 5 minutes to code this. we are going to go through this code together. I apologize if there was a lack of clarity on some parts of this, but what we're going to look at right now is I've already typed up all the code for what it will look like if we're just returning an integer with getAge. And we'll go through that code, and then we'll figure out how we can actually get it to align with what was asked of us to return an int star. So here's the code. And again, I apologize that we can't code this out as a group, but I want to make sure we get through it. So at the top, we have our function prototype getAge. We've seen that before. Return type first, then name, then parameters. Up here, we're including 3 libraries. Can somebody tell me what this line 12 does? Sharp include standard lib.h. What does that line do? If I were to ask you this on a quiz, and I asked you to give me the answer in 2 sentences, what would you say?
It includes library, standard library. Like it's the header file that allows you to use all the functions stored in that library.
OK, that's a good answer. It's the header function that has the prototypes of a number of functions. And if you're going to use those in your library, this is saying these functions exist. What else do I need to do if I'm including, say, the CS50 library? What else do I need to do when I compile my program?
You need to make sure to include it using the -L.
So we need to link in those CS50 library with -L standing for link. -L CS50 links in the actual ones and zeros, the actual implementation of, say, getString or getInt. So then we're in main. Ensure user entered one and only one command line argument. Just like our pseudocode, we have that if condition up here. Hopefully you guys are pretty familiar with this line and able to write this code pretty quickly, checking argc. Next, we're doing that A to I line. Again, you've seen that before. That's converting a string to an integer. Next thing I do is I have another if condition. I'm making sure they entered a positive number of dolphins per the specification, checking if dolphins is less than 1. So again, this first part of the code, these 3 things, checking if number of args, check the number of args, and if it's greater than 0. You've written this code a lot, validating user input. You should be pretty familiar with writing this code and being able to write it pretty quickly. Next, we're initializing a new array. What type of things are we putting in this array? Integers, per this first 3 characters. Next, we're getting ages. And a normal for loop, iterating through an array, and we're calling this function getAge, storing the return value of getAge in the array. Again, you've written code like this a lot before, too. One thing that hopefully you will glean from going through your past problem sets for this quiz is that a lot of what you're going to continue to do are things you've already done. It's very important to see those patterns so that you're not going to make your word super hard for you in the future by thinking, I've never done this before. You've done all of this stuff before. Next, our final lines of code. We're keeping track of the oldest age, going through each age, just like you suggested, Alden. And if the age of the current thing we're iterating through is greater than the oldest number we have stored, we update the oldest number. And finally, at the end, we print out the oldest number. Again, you've done this before. You've actually written linear search. You've written that. It was a little different. You were looking for a specific number, not the greatest one, but you've written this code before. And finally, in int getAge, you've seen this before. We have a do-while loop asking for user input until it meets a certain condition. And finally, we're just returning that integer. So all of this code you have seen before and written before. Nothing is new here. Of course, I presented it in a different way, and I maybe was too confusing with my directions, but you've seen this before. This logic, you 100% capable of. And if we run this program really quickly, I've already made it, so we'll run /trainer. What happened? I didn't give it any arguments. Let's train 5 dolphins. That'll be 1, 2, 3, 4, 5 years of age. And as you can see right here, it printed out the oldest age. So let's go back into gedit. But of course, this wasn't what the specification was asking for. It was asking for the prototype, not that returns an integer, but that returns an int star. So if I'm going to change it up there in the prototype, I better change it down here. And now let's work through this right here. Let's start at the bottom. Age is not an int star. Age is what type of variable? So line 63, age should not be an integer. It should be an int star. How do I make it an int star? Put a star there. And now let's look down here. 67. GetInt returns an integer. and we're storing that integer in age. But if we're treating age as a pointer now, how do we need to update this line? What? Put a star before age. Is that what you said?
Yeah.
Right? Because getInt returns an integer. We want to go to the location given to us in age and put an integer there. If we did this line of code, we'd be going back to what Curtis was talking about earlier. Saving in age some crazy integer, maybe the integer 5. Eventually we try to go to location 5 in memory, and we get in a lot of trouble for that. So we need that star there. And line 69, again, age, it's a memory address right here. So how do we need to update this line? Somebody else? How do we need to update this line?
Add an asterisk.
Exactly right. Add a little star right there. Now we're getting the value pointed to by age rather than age. So again, we saw this code go from integer to int pointer. Pretty similar. We need to look for all those places we had age, and we need to change them a little bit because we don't want to change age's box so much as what age is pointing to. And returning age, is that correct? That is correct because age is an int pointer. Yeah, question.
I have a quick question. Can we keep it like int age throughout, and then at the end put an ampersand in front of age?
And return its address?
Yeah.
That's an excellent question. You could do that, but we're going to let's get to that in a second and answer that question in a second. Fantastic question. Up here, if we're returning an int pointer, what type of array does what type of things is Dolphin ages storing in it? If we're returning an int pointer right here, what type of thing is Dolphin ages storing in it? Int pointers. So line 37 should be int star. That's the type of this array. It's not storing integers anymore, it's storing int pointers. And finally, down here, Dolphin ages bracket I. That's going to give us, again, an int pointer. We don't want an int pointer. We want the value pointed to by that int. So Assam, how can we change this line?
Star.
Exactly right. Put a star right there. That'll give us a value. What about line 51?
Another star.
Another star. That's exactly right. So we're treating, again, now these things as int pointers. Yeah?
Is it a problem at all that in getAge, instar age is never given a location?
It is a problem that instar age is never given a location, and it's going to be a similar problem to what you were talking about with just returning ampersand age and keeping it as an int. But I want to run this code first and see what happens. Okay, so variable age is uninitialized when used here. So it says initialize the variable age to silence this warning, and it suggests giving it null. Let's give it null. So we should get rid of that warning. We should be able to compile. Oops. How old is the Dolphin? Let's say 1. Segfault. So I would go through GDB now, and I encourage you to go through GDB on your own to figure out why this program just segfaulted. I'm not going to leave this as a cliffhanger, though, and I'm going to open up this function, and we're going to understand why this program segfaulted. So as you all know on the stack, when a function is called, a tray is added to the proverbial stack where local variables are stored. When that function returns, that tray goes away. Those local variables go away as well. Int star age equals null is a local variable saved in that stack frame. When this function goes away, this variable goes away as well. So we passed on the address of whatever. We passed on age. We took it, it's an address, we passed that on. But ultimately, sorry, I'm getting ahead of myself. Why this program really segfaulted in this case was because age was pointing to null, which is a specific location. And null is a location you're not allowed to touch. And so when we tried to write this line of code, going to age and doing something there, we got in trouble, and that's where we segfaulted. Because star age again is pointing to null. We went to null, which is a bad area. We tried to put getInt there, 1 in our case, and that's where we segfaulted. But say that had not been case. Say that we had given this a legitimate address right here, like BF4AC, something we saw before. Even so, when this program returned, we would run into a problem because that address would have gone away. The local variable address would have gone away. age, whatever age was pointed wouldn't have existed anymore. So the way we fix that is something you've seen before, the malloc function. And you've been introduced to that malloc function before. You've seen this? Malloc gives you some memory that doesn't go away when the stack frame goes away. So writing this line of code, and I'm going to give it to you for now, malloc, and since we're storing an int, we're going to malloc enough space. We're going to say, give me a box of size int. Malloc returns an address, and we're saving that address and age. Now when we run this program, we're not going to segfault because those blocks of memory we got through malloc don't disappear when the stack frame disappears. They live on until we want to get rid of them. And this goes back to your question, Jeff, from earlier. How do I create things inside of my how do I create things inside of my functions that I want to use later on in main or in different functions? I use malloc. And I pass them around. I pass their addresses around. That was a lot, admittedly, to cover just now. So please, if you have any questions, ask away. Yeah?
So malloc isn't on the stack anymore then?
That's exactly right. The box malloc is giving you is not on the stack. It's giving it to you in this other part of memory, which you're going to talk about in lecture on Wednesday. The name is the heap. But I don't want to talk too much about it other than it's this other place that doesn't get erased when the function goes away. OK. Any other questions? Avi.
Technically, if you didn't use a separate function and you put all of this code into main, would you still need to use malloc?
Great question. So if this is probably not the most efficient way of writing this program. You could have easily done this do while loop in main and saved yourself a whole lot of trouble. The reason why I wanted to do it like this is because I wanted everybody to be able to see how in main we can create an array of pointers, int pointers. We can initialize those pointers somewhere else, put them in this other area of memory that stays for as long as we want it to stay, and then we can access them later. For example, here we search through them. We could have done other things then. We could have gotten them and found the average. We could have done a lot of things. The point being that you can you can keep track of some things in main through an array, create those things somewhere else, and then still use them later on. And this idea, what we're doing now, is going to come up a lot in future p-sets and problems you want to solve. So that's why we did it like this, even though admittedly it's convoluted a bit in this context.
I just have a question about malloc again. So you know how I was saying, like, if you can keep all the int ages like as actual values as opposed to pointers, could you do the ampersand age now?
Sorry?
So like if you took out the stars on all of the ages and just did ampersand return ampersand age at the end, would that work?
So malloc returns an address.
Okay.
It returns an address. So age has to be an int pointer because it's going to be stored in address. OK. We have 6 minutes left. I'm going to skip talking about the stack for now. And I'm going to go into 3 minutes briefly on SPL, the most important things I think you need to know for the problem set. However, before I get here, because this is what we're going to finish on, 2 final reminders. One, admittedly, we went through things pretty quickly in this section. I apologize for that pace. If you have any questions about something we went over, why something worked the way it did, or something I did not explain as clearly as I could have, please shoot me an email or talk to me after class, and I'll be happy to explain it to you more in depth. So please reach out if you have questions. Again, the feedback website as well. Take some time after class if you have it and give me some feedback. I appreciate it a lot. As you saw at the beginning of class, I read through them, respond to them if you want a response, and I do take that to heart. That means a lot to me. So let's finish class by talking about the library you're going to be using this week. You've probably seen code like what I have on the screen up before. grect paddle equals new grect x, y, width, height. Now, you guys have probably, through reading through the spec, felt pretty comfortable with this. But for those who are left comfortable, or for you guys as well, I want to re-go over this line and see how it's similar to what we've used before. Just like with any variable, This is an object, but just like with any variable, we have the type first and foremost right here, grect. Next, we have the name of the object. And finally, we have the function that initializes it, gives us the paddle we want. Sometimes we write int x equals 5, and we initialize something directly. Sometimes we write string name equals getString. We use a function to get something, and we take its return value, and that's our new value. So we've seen this idea before where functions that may or may not need input actually create the thing for us, rather than us creating it directly. So we've seen this code before. Hopefully, this idea of an object, or at least creating an object, is not as overwhelming if you can conceptualize it as just very, very similar to things we've seen before. However, the cool thing about objects, is distinct from variables, is that we can do things with them. A variable, you can't change the color of a variable, but you can indeed change the color of an object. Or at least in SPL, you can change the color of your objects. You can't move a variable in a window, but you can move an object in a window. You can get an object's location. You can't really get a variable's location. That's the cool thing about objects in this library. However, these functions can be kind of confusing. We haven't really used functions or objects before. So I felt it was helpful to understand a generic way to express or do things with objects, or understand objects. And as you'll notice, I have two functions written here, functions you've seen before: add, window, comma, paddle, and set color, paddle, comma, black. In both these cases, we have a function that takes two arguments and does something. Now, more generically, all of these functions you're going to write that have to deal with objects take a what and a where, or a where and a what, rather. A where is the object you want to do something to. In this case, a window or a paddle. And the what is what you want to do to it or give to it. When you're setting the color of something, where are you setting the color? With the paddle object. And what color are you setting? Black. With the add function, where are you doing something? With the window object. And what are you giving to it? You're giving it the paddle. You'll notice that the functions you use, set color, set location, etc., all follow this pattern. They take something you want to do something to, the object you want to do something to, and what you want to do with it, or what you want to have changed, or what you want to have added, or the specific color you want it to be. Or if it's not filled, do you want to make it filled, etc., etc. So, admittedly, very brief discussion of the Stanford what is it? Stanford Programming Library? Portable Library, that's right. Thank you, class. Stanford Portable Library. So, but again, a lot more information is given in the problem set spec, but hopefully this makes it a little bit easier to understand objects, especially if they've been relating to things we've seen and done before. So with that, that is week 4. Enjoy learning about the heap tomorrow. Good luck on your quiz next week, but of course I will see you before then, hopefully in section next Tuesday. But also if you have any questions, comments, concerns, please feel free to reach out. And after class, I'll step outside if you want to talk about your problem set or have some questions.